Not so bad, not so bad. Wow. But be in the background. Okay. Ciao.
Francesco, do you hear me? We can start maybe. Okay. So my name is Carmine Maletta and I'm from University of Calabria, south of Italy. And I'm very honored to serve as a chairman of this paper session. This is the last day of the conference. And first of all, I would like to thank all the authors and the audience for attending this session. That is a very interesting one. These include 12 very interesting works that are mainly, whose topic is mainly related to generally to structural joining and welding. But before starting with the presentation, I would like to check if all the authors are online. That is to better manage schedule the available time. So if you are ready, I can check starting from the first one. The title of the first paper should be Simulation of Crack Growth in T-welded Joints, Residual Stress Field Effects, and the presenting author should be Ramalho. Are you here?
Yes, I'm here.
Okay.
Yes, I'm here.
So we will start in a few minutes. The second presentation should be given by Paolo Ferro. I saw it, yeah, him. So he should be ready for the presentation. Paolo, it's okay?
Okay, here I am.
So the third one is by Ashley Freeman, and the title is Examining the Effect of Indentation Separation, the Properties of Proteinaceous Adhesive Film. Ashley, are you there?
Yes, I'm here.
Okay. So the fourth is given by Song Wei. Song, are you online? Because we have two presentations by Song. Is there any other co-authors of these two presentations online? One is strength mismatch effect on residual stress of, and the second one is fatigue crack growth of chromium, nickel, molybdenum, and steel welded joints. Is there anyone there? No. Okay, let's wait a few minutes maybe. So the six should be 6 should be risk assessment based on analytical evaluation of structural integrity of drilling rig welded pipe. The presenting author should be Zaidi. Is there?
Alexander Sedmak will present it.
Okay. Thank you, Alexander. So and then numerical simulation of crack growth in welded joints with defects. Is there anyone from this presentation? Yeah, maybe.
There will be somebody, I'm sure, but they are probably late a couple of minutes.
Okay. And then automated implementation of the peak stress method for fatigue assessment of complex welded. Don't see the world title, but 90. The presenting author should be Vicentini, if
yes, I'm here.
Wrong. And is there? Yeah.
Yes, I'm here.
And then fatigue life estimation of welded steel joints under variable amplitude and so on. Vecchiaro or Base or Pagnolo and Meneghetti. Is there someone there? No. Maybe. And then there is another one, adhesive strength of an epoxy-based adhesive joint under complex stress state. Surgeries minor, Dimitri Konovola. Is someone there? No? And then influence of electrode wear on fracture of spot weld during shear tension test. No one? Preliminary finite element assessment of residual stress in dissimilar aluminum, steel, butt welded joints produced with the hybrid metal extrusion on bonding technique.
Yes, I'm here.
Okay, good. So there is maybe some missing others, but they are connecting in a few minutes, I hope. So before starting with the first presentation, I would just do a quick reminder about the suggested presentation method. We have a slot of around 10 minutes for each presentation. And the presenting author is encouraged to do a very short summary, a very quick summary of the work in, let's say, about 3-4 minutes. And the remaining 6-7 minutes can be used for question and open discussions. So to this aim, I encourage the audience to be active. So to ask, to ask questions to the authors. If we are ready, we can start with the first presentation. What's title is Simulation of Crack Growth in T-welded Joints, Residual Stress Field Effects, and presenting author should be Ramalo.
Yes.
Yeah.
Okay.
Thank
I
you.
will share my screen.
Yeah.
Okay. Hello, good afternoon. My name is Armando Ramalho, and I'm here to make a short presentation of the article Simulation of Crack Growth in T-welded Joints, Residual Stress Field Effect. The residual stresses affect fatigue life. Compressive residual stresses may be introduced intentionally by the components to improve their fatigue behavior. The presence of cracks at the weld toe influenced by the effects of stress concentration and residual stresses existing in the area affects the fatigue life of welded joints. In the study is presented a three-dimensional finite element method model that using virtual crack closure technique allows the evaluation of the influence of residual stress fields generated by overloads on the propagation of cracks on the weld of T-welded joints. VCCT is a local analysis technique that allows the evaluation of the stress intensity factor in the presence of residual stress field. This technique has been extensively applied in the analysis of delamination processes, mainly in two-dimensional models. Recently, we have used this technique in T-joints to evaluate the effect of residual welding stresses on the propagation of cracks in the weld toe using two-dimensional models. It was found that the residual stress gradients in the weld toe require great refinements of the mesh, requiring large computational resources. The use of this technique in three-dimensional models appears mainly with structured meshes with hexahedral elements and in simple geometries, or in full passing transverse crack in sync geometries. The mesh refinement required by the numerical model limited the analysis to the central part of the welded joints And even in these conditions, it was reached the limits of the computational resources of the used workstation. The crack growth uses automatic remeshing techniques over unstructured meshes of tetrahedral elements. Residual stresses are accounted for using superposition technique. The initial unstructured mesh is generated in MESC pattern. In this initial mesh is generated a semi-elliptical pre-existing crack. This initial crack is generated in MESC Mark software by a faceted surface through a remeshing process. The introduction of the initial crack promotes a great refinement of the mesh. This model will be subject to 3-point bending fatigue with pulsating nominal load in 3 different initial conditions. A, without initial stress field. B, with the tensile initial residual stress field generated by a compressive overload. C, with a compressive initial residual stress field generated by a traction overload. The overload causes plastic deformation at the crack front and in the weld toe that generate the residual stress field in these regions. The compressive overload causes tensile stresses that are taken into account as initial conditions on simulations B. The traction overload causes compressive stresses that are taken into account as initial conditions on simulation C. In the figures shows the evolution of the crack front along the simulations A, B, and C. The evolution of the crack front along the crack growth in simulations A and B maintains its initial semi-elliptical shape. The evolution of the crack front along the crack growth in the simulation C is completely different from the previous one, with the crack rest at surface and the propagation develops preferably in depth, occurring the tunneling effect. In figure are presented the fatigue results obtained in the various simulations. The effect of tensile stress field in the pre-cracked model, simulation B, is despicable. The effect of compressive stress fields in the pre-cracked model, simulation C, is very significant, with a great decrease in the crack propagation speed after overload. The fatigue slides obtained with the numerical simulation A were compared with the ones obtained by numerical integration of the Paris-Erdogan law, where the stress intensity factors are obtained by the MK factor proposed by Bonus and Lee. The results are shown in figure. The solution proposed by Bonus and Lee results more conservative with higher crack propagation speed. When compared these results with the experimental ones, it appears that the simulation A using the VCCT better fits the experimental results. As conclusions, we have the following. The developed finite element model reveals to be effective to predict the growth of cracks at the weld toe of a T-joint. The developed finite element model reveals to be effective to evaluate the influence of residual stresses generated by plastic deformation at the weld toe on the crack propagation speed. The compressive stress fields generated by overloads on the cracks propagating in the weld toe of T-joints promote the crack rest at the surface and tunneling effect on the crack growth. The tensile stress field generated by overloads on the cracks propagating in the weld toe of T-joints have a despicable effect on the crack growth. Thank you for your attention.
Thank you for your interesting presentation. We are a bit late with the schedule, but we have time for a couple of quick questions. Is there any question from the audience? Do you hear me? If not, I can just ask you a couple of questions. So as far as I understand, you simulate the effect of residual stresses that are generated by overloads.
Yes.
Did you did you analyze the effect of residual stresses generated by the welding process?
Yes. This, as I had we have make two-dimensional simulation with the effect of welding stresses, the stresses generated by welding. But when we go to make the simulations in three-dimensional,
Okay.
is very hard, and this is intended as a future work. We will extend this model to the entire welded joint, and in the presence of the residual stress fields generated by TIG or plasma remelting improvement processes. But for this, we need larger computational resources.
Yeah, I see, I know.
Yes, but because with this limited model, we have generated 3-4 millions of elements, because with this technique, with unstructured meshes, we need very fine meshes.
Okay, okay, it's okay. Thank you, thank you.
Okay.
Is there any other question? If not, we can move to the second one that should be given by Paolo Ferro.
Thank you.
And the title is Setup of a Numerical Model for the Post-Welding Heat Treatment Simulation of Steel Joints. Paolo, are you ready? You can share the screen.
Yes, sorry, on camera ready. Thank you very much. Can you see my screen now?
Just a few, wait a few seconds. Seems that is starting to, I don't see yet, but maybe it's running. Yeah, now, yeah, you can start, Paolo.
Very good now, thank you. Okay, good morning, good afternoon, everyone. Okay, this is the title of my work. Sorry, I try to start in presentation mode. Okay, this is the title of my work. The title is Setup of Numerical Model for Post-Welding Heat Treatment Simulation of Steel Joints. The authors. This is the summary of the work. I try to briefly summarize what we have done. First of all, the introduction and motivation. We try to simulate the post-welding heat treatment of a welding joint. You know that when we weld such kind of, in general, during welding, residual stress arises that could reduce the fatigue strength in high cycle regime. So it is very convenient to perform post-welding heat treatment in order to relieve the residual stresses and therefore improve the fatigue life of the welded joint. So the goal of this work was to simulate this post-welding heat treatment in order to and validate the simulation by using experimental analysis. An experiment were performed by welding plates of as 355 steel joint, structural steel joint. The thickness was 5 millimeters, and the geometry of the joint was a T-joint, where we have performed only one pass, only one run in the one side of these T-joints in order to introduce a sort of angular distortion that was used to validate the model. So we didn't measure residual stress, we measured the distortion of the joint after welding in order to have a comparison with the numerical results. This table summarizes the process parameter used for the welding. We time of 3 hours and a temperature of 510 degrees. After welding distortion, in particular the angular distortion, that was managed with a computer in order to calculate the angular distortion that you can see in the left side of this picture. This is the model, the numerical model. Was performed by using Syswell numerical code. We divide the element in 2 different groups: the base material, the parent materials, in that they are colored in white, sorry, and in blue you can see the element that we use to simulate the bead. And these elements are activated when the source came over the elements. We use as a source the very famous Goldak heat source that has a double ellipsoid distribution function, power density distribution functions. After welding, we perform a numerical simulation of the post-welding heat treatment, the stress relief heat treatment. This is the recipe, the furnace, the recipe that we impose to the mold as in the experiment. And we implement and we use this kinematic creep law in order to assess the stress relief during the heat treatment. The parameters of such a model are obtained, are taken from literature and from Syswell database. These are the thermal result in your left, and you can see a comparison between the dimension and shape of the fusion zone calculated by numerical analysis and by experiments. And also the length of the tail of the fusion zone is compared with those obtained by experiment, sorry. And in your right, in the right side of this picture, you can see also the metallurgical result. And we found in the fusion zone a ferritic structure composed by a basket-shaped ferritic grain, and with that is typical microstructure of a very low carbon steel used as a filler metal in these joints. And in the red zone are the zone where we found the greatest amount of Finite, and we also have found a good correlation with the experiment. You can see a good correlation between numerical and experimental analysis in terms of metallurgical or phase distributions after welding. We compare the angular distortion of the the welded joint calculated by experiment and numerical analysis, and we found a good agreement between the two measurements in as welded condition. It is important to say that we also calculated the angular distortion after the stress relief heat treatment, but we didn't find any change. So both in experiments, we didn't find a variation in angular distortion after the stress relief heat treatment. In any case, with the software, we are able to calculate the distribution of residual stresses. And so in this distribution, residual stress distribution of the as welded joint and the stress relief joint. So we found a good variation in this case, but we didn't have the possibility right now to calculate the residual stress. But these issues it was planned for the next work. So in the next work, we planned to perform also numerical, experimental determination of residual stresses. So these are the conclusion. I can see that. I think that it is found. Oh, sorry, that we found a good correlation between experimental and numerical analysis on the one side. On the other side, this work will going on. We found good correlation in terms of this talk. Okay, this is all for now. Thank you for your attention, and I'm here to your question.
Thank you, Paolo. Very nice presentation, very interesting work. We are still late, but we have time for a couple of quick questions. Is there any question from the audience? So if not, I can just ask you a couple, just a curiosity. You did simulation by Sysweld. It's a commercial software, if I'm not wrong. I'm not familiar with this software, but the curiosity is, are you able to simulate the development of residual stresses? You simulate the process, so including development of residual stresses, and then by starting from this point, end of the process, you do thermal treatment, isn't it? In just one simulation. Do you hear me, Paolo? There is maybe the connection is not so stable. I don't hear you. Do you hear me?
Yes, of course. It's correct. It's correct. Yes.
Yeah.
Can you hear me?
Yeah, I do. Yeah. There is maybe some problem with the network. It's not so stable, the connection. Anyway, yeah, Paolo?
Yeah, can you hear me now?
Yeah, now, yes.
Okay, yeah, it is correct. Your observation.
Okay.
We perform the numerical then.
Yeah.
Yes.
Yeah, it's better.
I can hear you.
Yeah.
So it's correct, your observation. We perform a numerical simulation of the entire welding process, and then we use the result for the calculation of the residual stress relief.
Good.
Yes, it is possible to do in this kind of simulation in sequence.
Good. That's okay. That's why. Okay, maybe you can also in this way analyze the effect of welding parameters on the residual stress development. It's a very nice, very interesting work. Thank you, Paolo.
Thank you very much.
So we can move to the next presentation, which should be given by Ashley, and the title is Examining the Effects of Indentation Separation on the Properties of Proteinaceous Adhesive Films. Ashley, are you ready for the presentation?
Yes, I'm ready.
Thank you.
I am one of the authors on examining the effects of indentation separation on the properties of proteinaceous adhesive films, which is just a fancy way of saying we were testing gelatin-based adhesives made from bone glue of a cow. And the reason why we were doing this with indentation is that typically when we're looking at cultural heritage materials, such as what you can see in the lower right-hand image, of a painting in a stave church. So it's a Norwegian wooden medieval church. These types of materials, because of ethical reasons, we can't sample large quantities. So typically we have sub-millimeter size samples, as you can see in the lowest image. So the idea here is to test these adhesive films at the same scale length, so indentation, as the distempered paint or the paint that is bound in these types of adhesives. So what we did is that we made glue or an adhesive from bone of a cow, and then we adhered that to a metal slide, which you can see a schematic in the lower left-hand image. And so the entire idea is when we are indenting, we would like to see how many indents we can get in one area without affecting the actual obtained modulus or hardness values. So to do that, we need to look at the separation between the indents, so the sequential indents that we did. And so we did 3 different orientations. It will let me go to the next one, which you can see, hold on, in the lower right hand in this red box. So what we did is we did it in the X direction. So the spacing varied between the indents. So if we had indent 1, 2, and 3 in the X direction, so the first schematic, this separation would be the same. So it would be either 3 microns up to 100 microns. Then in the Y direction, so this is the didactic in the middle, and same, so it'd be 3 microns to 100 microns. And then we did a 3x3 matrix. So in between each indent would have the same separation. So from this case, it would be from 6 to 35. And when doing this, we actually noticed that around a separation of 14 microns between the sequential indents is when we start to get relatively similar data, which then means that we can space our indents by 14 microns or greater, allowing us to have comparable data and therefore a larger statistic within our small samples. And that's the end of mine. Are there any questions?
Thank you for the presentation, Ashley.
Sure.
And yeah, is there any question from the audience? If not, just a very quick question. I see that the total thickness of the layer is 100 micron, isn't it?
Yes.
And yeah, a few information about the loading parameters. I mean, maximum load, type of indenter, and so on.
So the maximum load for these tests was 10 millinewtons. So the linear loading, we did a linear loading of 1 second and then a 0.5 second pause. So I can show you the actual schematic because it'll be easier to say it when you see it. So here, so a linear loading of 1 second, 0.5 pause, and then a linear unloading of 1 second. So then the max load of 10 millinewtons. And then typically what we're having is we're staying within the rules, the 5%, 10% rules. So for this case, we got a little bit deeper. So if the indents got deeper than what should happen, we didn't actually use that data set because we were trying to look at these as if they were also a coating so that we didn't get any substrate effect.
Okay. I see that the maximum depth here is around 1 micron, isn't it?
Exactly. Yes.
Yeah, it's good. Thank you. Very nice.
Thank you.
Is there any other question from the audience? So if not, we can move to the fourth presentation. That is, the author should be Song. Are you there? Song?
Yes, I'm here.
Yes.
Can you hear me?
Yeah, I hear you. Yeah. The title should be Strength Mismatch Effect on Residual Stress of 10 Chromium, Nickel, 3 Molybdenum, Vanadium, Steel Multipass Path Welding Joints. You can start with sharing the screen and with the presentation.
Oh, okay. Wait for a moment. Can you see the presentation now?
Yeah.
Okay. Thanks for the listener. It's with my great pleasure that I'm presenting the talk today. The focus of my work, my talk will be on the strength mismatch effect on the residual stress of steel multi-pass but welded joint. This work of the background and the motivation for the work, as many you can see in the presentation. One of the effective way to enhance the lightweight of the structure, to increase the strength of the steel, and for decreasing the thickness of the plane, and it is dealing with the conventional material. How about the structure performance, especially for the welded component? There's no corresponding the welded failure for the high strength steel or the very high strength steel. So, however, for these components which are driven by cyclic loading, off-peak loading, there is a unique opportunity to utilize the high strength steel and investigate the performance of the special weldment. So we choose some the undermatched weldment to solve some problems, such as the hydrogen-induced cracking or softening of the HAZ, head effect zone, or the declining of the softness of a welded joint. So we sort of we have two different ways to solve the problems, such as from the welding processing or the welded material. So we use the undermatched weldment failure to weld the high strength steel. How about the residual stress of the welded distribution of the welded stress? And the rest, as we all know, the residual stress has influence on the performance of the welded joint component. So the study aim and investigate the residual stress distribution of even matched weldment and undermatched weldment. During the simulation of the welding processing, we consider the SSPD effect on the residual stress distribution for the even matched welded joint, and also the backtipping processing effect on the multi-pass processing are considered in the simulation. I think it is very useful to access the integrity of the welded structures and the optimization of the welding processing for the welded structure manufacturing. So the experiment, the basic mechanical properties of the materials are presented in this page. So we used the base metal about 700 megapascal, and the unmatched weldment is the about the 500 megapascal. So the even matched welded the even matched weldment is presented is the same with the base metal properties. So we test we measured the residual stress of the different welded joint using the deep small hole method. So and during the FEA processing, we consider the back chipping processing. So which is presented in this page. And during the simulation, we considered the phase transformation. Yes, we consider the thermal field and the mechanical field and the metallical field interaction between among them. So we test the different material properties of high and high temperatures. So such as the CCT curves or the phase transformation curves, and the yield stress and the different high temperatures. So we write the user subroutine to simulate the residual stress and the deformation. Consider the multi-pass processing. So this is the even matched welded joint, which from the result we can see that the coated residual stress based on the SSPT model are selected underestimated in the fusion zone compared with the experimental data. Also, we can see in the transverse residual stress direction, the experimental data agree with the experimental data. So this is the undermatched welded joint. Because there's no SSPT effect in the undermatched weldment. So the residual stress near the interface exists a great discrepancy attributed to the due to the residual stress, the yield stress mismatch of base metal and the undermatched material. Also, we consider the back chipping effect. So I think the residual stress distribution of the back area cannot affect and its variations of the front surface in the welded plane after the back chipping processing. This is my conclusion about the investigation. The first one, considering the SSPT effect and the yield stress variation in the welded processing effectively, it enhanced the computational precise of the residual stress. The second is that the mismatch effect of material yield strength on the residual stress distribution is more significant for the longitudinal direction residual stress than the transverse direction. So the residual distributions consider the SSPT effect where is that a considerable contrast in both directions by comparison between the even matched and the undermatched welded joint. The third conclusion is about the back chipping processing in the multi-pass welded joint show a great influence on the final residual stress distribution. It's not only alert to the residual stress distribution tendency, but also change the maximum magnitude of the back welding regions for the even matched welded joint due to the SSPT effect. Okay, thanks for your attention.
Thank you, Song. Thank you for your interesting presentation. Is there any question from the audience?
Yes, please.
Yeah, Alexander?
Yes, having in mind the title and the practical point of view, can you tell us in one sentence what is the effect of undermatching on the residual stresses? It looks like that residual stresses are higher with undermatching effect, but I'm not quite sure because you considered many parameters. So please tell me, as from engineering point of view, about the effect of undermatching on residual stresses.
The undermatched materials affect the residual the maximum residual stress value. So as we can see during the due to the SSPT effect for the undermatched weldment, the residual stress is lower than the undermatched weldment. So I think the undermatched material yes affect the maximum magnitude of the residual stress.
Will it increase? Will it increase residual stress or decrease?
Yes, a little bit. It's a near the yield stress of the undermatched material.
So it will increase. Okay, thank you.
Okay.
Thank you. So we can move to the next presentation. The title is Fatigue crack growth rates of 10 chromium, nickel, 3 molybdenum, vanadium steel welded joint considering the stress ratio. And presenting author should be again Song, if I'm not wrong. Isn't it?
Okay, thanks. Also my presentation. So in this part, I just do some. I did some fatigue crack growth experiment about the material and the undermatched material, considering the stress ratio. So I now I did want to. So I think it is not necessary to introduce the background and the motivation of the study.
Yeah.
Just one part of my whole project. So the study of M and investigating the fatigue crack growth property of base metal and the mismatched welded metal. Also the stress ratio and the pH picked up the post heading welding treatment effect on the FCGR of the materials. And finally, I analysis the FCGR mechanism of the base metal and the mismatched welded metal. So the material is the same with the last presentation. So I choose the CT specimen for the FCGR FCGR experiment.
Do you have some slide to show to support your discussion? No.
Okay. The material mismatch and the pH-WT effect have obviously effect on the FCGR data of CT specimen and the ratio 0.1. As we can see, the last one figure. So the even matched, the undermatched I think the even matched have a higher the undermatched undermatched development has higher fatigue growth ratio rates than the even matched development. And also we did we analysis different ratios for these materials, such as the 0.1, 0.2, 4, and 0.7. So the material ratio have obvious influence on the FCGR data for the FCGR properties. Because of the residual stress in the during the environments. So I think as we all know, the tensile residual stress will illustrate the FCGR, and the concept and compressive residual stress will redundant the fatigue propagation. So look at the residual stress distribution of the even match and the undermatch. The longitudinal stress is crucial for the FCGR behavior on the basis of the extracted direction of the CT specimens. So the comparison between the experimenter and the calculated residual stress can give a good algorithm prediction. So I analyzed the fatigue crack path and based on the EBSD analysis and the plasticity of the environment. Also, the typical fractal graph of even matched and undermatched are presented in this page. So I think the conclusion about the study of this part, for the low residual stress, the undermatched demonstrate higher FCGR curves than the BM and the EWM. So there's no significant difference of FCGR for even matched and undermatched development between the high stress ratios. The second is the two different fracture mechanism are exhibited for even matched and undermatched development. Transcalar fracture appearances were showing on the even matched development, while the intergranular fracture surfaces were observed on the even undermatched development. So the FCGR under the S-welded state is slightly lower than the PWHT state, attributing to the tensile residual stress effect on the FCGR on the fatigue property. Okay, okay, it's over. Thank you.
Yeah, I'm sorry to stop you, but I invite you, all the others, to keep the presentation time limited to 3 or 4 minutes. Otherwise, we do not have time for discussion. unfortunately, we have to move. We are late. We have to move to the next presentation. Thank you again, son.
Okay.
And,
Okay.
yeah, next presentation is risk assessment based on analytical evaluation of structural integrity of drilling ring welded pipe. And the presenting author should be, if I'm not wrong, Alexander Sedmak, isn't it?
Yes, you are right. Let me share the
Thank
screen.
you. Thank you very much.
You're welcome. Can you see it?
Not yet.
Not yet.
Yeah.
What's going on? Sorry for this. I see it and something strange is going on. I lost my commands.
The green button.
Yeah.
Let me try again. Share screen. Okay. It wasn't actually reacting on previous pressing. So share. Do you see it now?
Slowly. Yeah.
Yes.
Good.
Okay. Thanks.
So the presentation is about risk assessment, mostly based on analytical evaluation of rig welded pipe. No, I didn't want this. I don't know how to stop this. Sorry. Can you hear me now?
Yeah.
Okay. So
Yes,
risk-based approach can be quite complicated, but here we use a simplified version. I would call it engineering version with application of the risk matrix. And concerning the basic definition of risk as a product of probability and consequence. So for low probability and low consequence, risk is also low. And then for high probability and high consequence, risk can be extreme. All other combinations are in between, and we usually present them in a way of a matrix, risk matrix. For the consequence, which we will not discuss in this presentation, we can use also different ways to estimate it. And you can see in this table what are the possibilities. So we look at people, property, environment, reputation, and maybe some other effects as well. And then we can estimate the consequence. Anyhow, in this paper, consequence will be fixed. I think it is a moderate one, and we will focus on probability. Now, probability is a mathematical term, but it should not be taken literal in this case. We will use relatively new definition, one for static, the other for fatigue loading. For the static loading, we will use failure assessment diagram to estimate probability, and that will be the ratio between 0 to A and 0 to B. I think this figure is self-explanatory, as well as the other one where this probability is simply the ratio between already used number of cycles and fatigue life. Logic is very simple. If we are here at failure assessment diagram close to 0 point, then probability is 0. And if we are at the limit line, then probability is 1. So those are, once again, engineering. So the case study which illustrates this is oil rig drilling pipe. Data is shown here about material and some service conditions. And main characteristics are provided in this slide. So we need to know the pressure and number of strokes for the fatigue loading. You can see in this sketch that artificial crack was made in this prototype with length of 200 millimeters and depth approximately half of the thickness, that is 3.5 millimeters. Now to evaluate the stress, I have troubles with this voice, which should not be heard, but anyhow, here you can see a lot of formulas which are used to evaluate stress intensity factor for axial surface crack. And then we use data obtained here to get the point on failure assessment diagrams. You can see here at the bottom which pressure we have used. One is 10 megapascals, which is operational, and 22 was testing pressure. So for these two pressure values, we get 2 points. Both are inside the safe part of failure assessment diagram, as you can see here, but one with relatively low probability and the other with relatively high probability. And then for the fatigue, we simply use Paris law. With some simplification, we can integrate it directly to get number of cycles, which is not very precise, but it is conservative and, of course, in engineering term, usable. So here are the results, which are in the terms of number of cycles versus critical, number of cycles versus load, cyclic load, and length, initial length of a crack. So when we put all these together in the risk matrix, we can see that we have for the consequence category 3, or moderate consequence, we have here quite low risk for cracks which are relatively short, and then moderate risk, and then high risk for long crack, and of course high loading. I think we can skip this and go to conclusions. So I have shown a simple engineering approach which can tackle both static and dynamic loading and get some quite simple answers, which might be over conservative. In that case, we will turn to finite element method to get more precise analysis, but basically the principle is the same. Once again, we will directly integrate Paris law and use failure assessment diagram. And finally, what is important is to notice that risk-based analysis is a useful method to provide gap between engineers and managers, because engineers know what it is about and managers know what they want. And that is often in conflict. So there is a gap in these two minds, and to provide a bridge over that gap, risk-based analysis can be very useful. Thank you.
Thank you, Alexander.
Okay, any questions?
Yeah, thank you for the presentation. Is there any question about it? If not, okay, just a quick question, just a comment.
Yes.
I see it is a very interesting work, I mean, with a very high practical interest, industrial interest. And I was wondering if there is some limitation related to the standard, the design standard to be used. If you, I don't know, if you can do some, okay, discuss about it.
Yes, yes, I can make a comment on that. It's actually a very good question. For the consequence, I showed this complicated scheme, and that is more or less according to a standard, let's say API 581. But there is also ISO 30,000 series of standards for risk. And there are basically three methods how to evaluate probability or frequency of events. One is too simple to be real. It's just the number of events divided by the number of total events, but that is really nothing. The other is, on the other hand side, too complicated. It is about the thick handbook, how to make a survey with employees and survey on everything that happens in a company. And then after 1 week, 2 weeks, or 1 year, you will get an answer. And what we rely on is the third option, which says you can use expert opinion. And I believe this is expert opinion. It's relatively simple, and we can use it in a couple of hours, not
scientific stuff at all. I mean, not scientific. Yeah. Thank you for the presentation.
Thank you, Carmine.
Thank you. So we can move to the seventh one, that is numerical simulation of crack growth in a welded joint with defects. And is there someone for this presentation?
Yes. Can you hear me?
Okay, you can. Okay, thank you. You can start.
Okay. Do you see the screen?
Yeah, I see.
Okay, so my name is Simon Sedmak, and today I will give a short overview of this presentation, which involves the research which we're currently doing with the first author of the paper, my colleague and friend Mihailo Rangelovic. It involves the effects of the presence of multiple different types of defects in a welded joint. Generally, the ones that occur frequently in practice, because current standards only deal with one defect at a time, and we wanted to see how different combinations could affect the geometry and the integrity of the welded joints. And for this purpose, we welded some plates using typical structural TOS 235, and then decided to make some numerical simulations of different cases, while at the same time performing various experiments so we could validate this approach and see what we can basically expect depending on different combinations of defects, which generally included misalignments, excessive weld metal, undercuts, incomplete root penetration, and anything else that tends to appear frequently during the practice. So here you can see how we prepared some of the welds. Here there is the actual 2 millimeter misalignment, which we suspected would have a very adverse impact on the structural integrity. And here you can also see how they were welded. One half of the plate would have one combination of defects, and the other half would have a different combination, and then specimens would be later cut and tested. So here you can see all of the combinations of defects, which I had already mentioned. Won't go into detail too much about that. And the first stage was to make the models based on the real geometries in Abacus. And here you can see an example of one of these models with the excess weld metal, the undercut, and the incomplete root penetration. With its boundary condition, it was fixed on one end and subjected to tensile loads on the other. And here you can also see the mesh. Now, these are the results for the different cases. These are this, for example, is one of the misaligned cases, and this was the other one. And you can see the stress concentrations in the more or less expected locations, where there were sharp geometric transitions. but also slight stress concentrations in the undercut as well. And here is an example of one of the non-misaligned specimens that only had well metal sagging and incomplete root penetration, and of course significantly more favorable stress distribution. The next stage would involve that once we determine the locations of stress concentrations would be to include initial cracks in these areas to see how the welded joints would behave under those conditions. And here you can also see in more details the stress concentration. For example, in the misaligned case, there was the maximum values of the stresses were around 240, while the yield stress of the parent material where this concentration occurred was 235. So there was plastic strain in this case. In any cases that didn't have the misalignment, the stresses were higher, but they were concentrated in the weld metal, which was much stronger. So there were no plastic strains, which would result in the cracks. So actually here, the goal was to determine the locations in which the cracks would later be introduced and observe the behavior later, while also validating this using tensile tests. Now, this was a couple of months ago, and in the meantime, a lot of things have happened. The models have been tested, and most of our assumptions were verified about the behavior in terms of stress concentration, except for some other models where we got a bit different results and concluded that we need some more detailed tests like macrofructography to determine what was the cause. We already established that, but that will be for some other opportunity. And now we're going to be doing the same with a slightly different material, while also making the similar combinations of defects. Actually, they are being welded and tested as we speak now. So in general, this is just the introduction part of a very interesting research that keeps giving us unexpected results, and we hope that we'll be able to explain the behavior of each of these combinations of defects and see which of them are more or less favorable. So basically, that is our current work in short. Any questions?
So here we are. Any question?
Yes, Carmine, I have a question.
Yeah.
Thank you very much for the nice presentation and talk. And this is really interesting, and I think it's worth of investigation. So I would like to ask if you have any plan to extend the methodology to multi-axial loading, because I have seen that it's quite well established for tensile loading, but I would like to know if you have any plan for an extension to the multi-axial case.
Well, that's not a bad idea, actually. So far, we're mostly sticking to tension, although this actually is a bit multi-axial because of the geometry with the misalignment.
Yeah,
when you put them in the tensile test machine, it deforms a bit differently.
Exactly.
So that could be an interesting idea at some later point.
Okay.
Yeah.
Thank you so much.
Thanks. But you did, if I understand what you did, just you did to the analysis, isn't it?
Yes.
Or no? So the effects of thickness. I mean, you did the plane strain or plane stress.
This should be, since it's 2D, this should be plane stress. We will probably at some point make 3D for plane strain as well. To see if something happens in between. Because the crack will never grow perfectly flat through the.
Yeah.
If we go in that direction.
Yeah. Thanks. Okay.
You're welcome.
So we can maybe move to the next one. That should be the title should be automated implementation of peak stress method for fatigue assessment of complex welded. I don't see structure.
Yes.
Someone for this paper presentation? Alberto Vicentino. Okay.
Yes, I'm here. I share my screen. I need the yes, because that's still the latest participant who is sharing, so he needs to.
Can you stop the share, the screen sharing?
Simon, you have to stop the.
Simon.
Yes, I'm sorry.
Yes.
Just a second.
Stop.
Thank you.
Thanks.
Yeah.
Yeah.
Okay, so I share my screen.
Yeah.
Okay. Okay, so you should see the presentation. Good afternoon to all of you. I am Alberto Visentin from the University of Padua, and I'd like to start with some highlights on the work entitled Automated Fatigue Implementation of the Pick-Stress Method for Fatigue Assessment of Complex Welded Structures. So these works deal with the development of a new application called ANSYS PSM within the ANSYS Workbench FE code, with the aim of automating the fatigue strength assessment of complex welded structures according to the Pick-Stress method. So we developed and tested the ANSYS PSM app on complex welded structures commonly installed on roller coasters by Zamperla, the famous amusement ride company. As in the example reported here, where fatigue life can be plotted along the analyzed model edges thanks to the automated implementation of the Pick-Stress method. So the starting point of the fatigue assessment workflow is a solved finite element analysis. So generic loads and constraints can be applied to the model, and a mesh composed by 10 nodes tetra elements needs to be generated. Once the solution is done, we can apply automatically the Pick-Stress method to the structure under XM, taking advantage of the ANSYS PSM app. Moreover, taking advantage of the results coming from the automated implementation, we can define new fatigue classes and the categories, for example, for complex geometries, which do not necessarily have comparison classes in international standards and recommendations. So let's take a simple example to see how the app ANSYS PSM works. The example reported here is a complex welded structure taken from this lattice type model commonly installed on roller coaster structures. It is an arc welded steel joint, and the model has been simulated taking advantage of a submodeling technique. So the app needs to asks the user to complete a setup menu, collecting information about element type, material settings, and geometry properties, which needs to be input by the user in order to start the automated analysis. The app prompts a series of automated checks and also allows the user to select the desired fatigue design curve and survival probability for fatigue estimations. Moreover, the user can select a set of target edges, as you can see. The app will focus on during the analysis in order to reduce the computational time. Once we hit finish, the app starts to evaluate the model, applying the Pick-Stress method, and it can complete the analysis on this model in barely 12 minutes. At the end of the elaboration, we can plot all the different fatigue life results on the model's lines, taking advantage of custom results, which has been developed accordingly in order to show all the fatigue life results along the model in this wireframe view. So with this, I have completed my highlights, and I'm open for any question.
Thank you, Alberto. Very, very nice, very interesting presentation. And is there any question from the audience?
Yes, Carmen, I have a question.
Yeah.
Thank you very much for the presentation. I want to ask if this feature that has been developed inside the ANSYS is because I know that the Pick-Stress method needs a kind of is connect with the element that you are using. So is the application able to that according to the element that you are using to select the appropriate shape function that you have to use for the application?
So the app is able to recognize the element type which is used in the structure, and according to the element type which has been used, the app automatically references all the calibration constants and parameters the PSM requires for the calculations.
And another curiosity is how you can apply the, of course, this is good for uniaxial. When you have a multi-axial case, can you extend the method, or there is a perspective to extend this application to the multi-axial case?
Well, the application already analyzes every possible structure with the generic load conditions. You can prepare a model with the loads and constraints you want and simulate it. After the simulation, the app works as a post-processing subroutine, we can say, and analyzes the different V-notches, recognizes and analyzes the different V-notches in the structures. So you can actually create a model with the different loads and constraints you want, and the app works independently from it.
Okay, thank you so much. It's very nice. Thank you.
Thank you, Alberto. Thank you.
Thank you.
Yeah, I agree.
Thank you for the attention.
So just another curiosity, very quick one. Are you managing to include this app, this method in a future release of the commercial software of ANSYS or not?
At the present moment, we do not have agreements, we can say, with ANSYS for including it in the real release of the software. But we are eventually thinking about letting the app, making the app available through the ANSYS store, the ANSYS App Store.
Good.
So there's this App Store, and you can make your application available for other users who can download it and integrate it in their installation of ANSYS Workbench.
That would be very nice. Great. Thank you again. Thank you again.
Thank you for the attention.
So we can move to the next one, presentation, that is fatigue lifetime estimation of welded steel joints under variable amplitude loadings using the peak stress method. And is there anyone?
Here I am, Luca Vecchiato.
Hi, Luca.
Can you see me? Can you hear me?
Yeah, yeah. You can start sharing the screen.
Let me share the screen. Can you see the presentation?
Yeah.
So good afternoon, everyone. I'm Luca Vecchiato, PhD student at the University of Padua. The work has been conducted in collaboration with the master student Beatrice Besa and my supervisor Alberto Campagnolo and Professor Giovanni Meneghetti. It's related to an application of peak stress method, the same method presented by my colleagues Alberto Visentini in the previous presentation, to fatigue life estimation of welded steel joints subjected in this case under their variable amplitude loadings. Just to sum up what the method is related to, it's referred to local approaches for fatigue life assessment of welded joints, and in particular, it assumes that the weld tool and the weld rod can be modeled as sharp V-notches. Accordingly, it has been shown by many papers in the literature that the notch stress intensity factor is a fatigue relevant parameter. And moreover, in 2007, Professor Meneghetti and Professor Lazzarin defined the so-called peak stress method as an engineering tool to rapidly estimate the NCs at the V-notch tip by means of linear elastic finite element analysis with a rather coarse mesh if compared to the one required by for computing the NC by its definition given by Ross and Magnuson. Adopting as a fatigue damage parameter the strain energy density averaged over a circular sector of radius of 0 at the V-notch tip, as proposed by Professor Lazzarin almost 20 years ago. It has been shown that if in the case of negligible high order and non-singular stress terms, the SED can be written as a function of the NCs. And by combining the strain energy density approach with the peak stress method, it has been shown to be possible to define an equivalent peak stress as a fatigue damage parameter. In particular, fatigue design curve for prevailing mode 1 has been proposed in the literature and in the reported paper. And it's the one reported in this slide. In this context, the aim of the work, the presented work, was to trying to extend the formulation of the peak stress method not only for constant amplitude loading, but also for variable amplitude loadings. And to do so, the idea was trying to preserve the simplicity of the method, and it was chosen to combine the peak stress method formulation for constant amplitude loadings with a linear cumulative damage rule as proposed by the Error Code 3. The consequent procedure is quite simple to be applied and preserve the simplicity of the method, also shown by my colleagues Alberto Visentini. The first step is to have known the nominal stress range spectrum and the local geometry of the welded details, as in the example. The second step is to apply the peak stress method for computing the singular stress at the V notch tip, the nodal value of the V notch tip. And then combining the fatigue strength criterion of the strain energy density, is it possible to define the equivalent peak stress range for every peak nominal stress range for the spectrum? Please note that for define the equivalent peak stress spectrum, only one linear elastic finite element analysis is required. Then the last step is just the adopting the cumulative damage rule, the linear damage rule, and so it is possible to define a constant equivalent constant amplitude peak stress range. Just to check the validity of the proposed method, some data were taken from the literature and in particular from the reported reference by Sonsino, Kaufman, and many other authors that work for European work together, European research program together. In this work, they tested many different welded specimens. In particular, they were made of 4 different geometries, made of 4 different steel grades. And all these specimens were tested under 3 different load spectra, in particular, constant amplitude loadings under Gaussian standard load spectrum, and also Gaussian with the overload spectrum, both at fully pulsating loading and fully reversing loading. So at the load ratio R equal to 0 or R equal to -1. The results were reformulated, were recomputed according to the procedure we have seen before, so according to the peak stress method, and the results are reported in the 2 charts below the slide. At the left, on the left side, are reported the constant amplitude data that are not fitted on the scatter band, which is the PSM, the Mode 1 design scatter band, and also on the right of the slide, we can see the results for the variable amplitude data. We are seeing almost 200, more than 200 variable amplitude data that have been reanalyzed according to the peak stress method. So that's all. If you have any question, I'm pleased to answer.
Thank you, Luca, for the interesting presentation. Is there any question?
Yeah, I have only a curiosity about the size in terms of elements of the models that you have carried out to perform this research. I think if you can give us a kind of idea of this, would be nice. It's only to understand that it's.
Yes. Thank you, Professor Berto. Nice to meet you.
Yes.
Just let me find the example I've reported in the full presentation online. The adopted meshes is a 2D finite element model with the element size of 5 millimeters.
Okay, perfect. Yes, but have you a plan to extend this to a 3-dimensional case when necessary?
Yes.
Or you are?
We have yet extended also for any kind of meshes type. So according to the automated procedure we have seen with Alberto Visentini in the previous presentation, and we are also trying to extend the formulation for multi-axial variable amplitude loadings. In the near future, the procedure will be published.
Okay, and the last curiosity.
Yes, please.
Did you detect some difficulties to assess the fatigue load at low cycle, or is quite easy also for that case? Did your analysis affect a bit from plasticity in some cases, or everything is fine?
Well, thank you for the interesting question. Up to date, we have not analyzed yet the effect of low cycle fatigue on this procedure. We have just limited the application to literature data and for medium high cycle fatigue. Well, it would be very interesting to assess the fatigue life to trying to apply this procedure to low cycle fatigue. Probably it would be some sequence effects to be taken into account also.
Yeah, thank you so much. I think the work is very good. Actually, is excellent. Thank you.
Thank you.
Thank you, Luca. I have another quick question for you. Just a
Yes,
curiosity. I'm not familiar with the PSM method, but it's very nice. I will try to read something about it. And yeah, my question is, if you have residual stresses in the welds, how do you manage this? I mean, are you able to take into account the presence of residual stress in the welds by the PSM?
Up to date, there are many works on it. My colleagues are trying to publish or are publishing work on effect on HFMI welded joints, so taking into account residual stresses, but there are still works to be done. There is the possibility to take into account also mean stress effect for stress relieved joints, but for the as welded case in the application does not take into account residual stresses.
Okay, thanks. Thanks again.
Thank you.
So, any other question? If not, we can move to the next one. That should be adhesive strength of an epoxy-based adhesive joint under complex stress state.
Good day. My name is Sergey Smirnov.
Hi, Sergey. Okay. You can share the screen.
You see?
Not yeah.
Yes.
Okay.
The theme of my
we would like to present our research work, the effect of stress state on the adhesive.
I'm sorry. Adhesive strength on epoxy-based adhesive joint under complex stress state. The development of methods of evaluating various performance characteristics of adhesive joints is becoming important since it will enable us as early as a production stage to predict the ability to resist loads without failure. The aim of this study is to test a modified Arcan device to investigating the effect on the stress state on the adhesive strength of the epoxy aluminum alloy junction. Polymer interlays were made from a glue based on ED20 epoxy. The substrate system was produced from a hot-rolled plate made of aluminum, magnesium, lithium alloy. In figure 1, we see a general view of the test specimen. The prepared specimen were mounted in the grips of the testing machine, and the angle alpha between the tensile direction and the normal of the junction plane was varied. The change of the load P was recorded during the testing. Failure occurs within elastic deformation of the epoxy layers. The values of strain, energy, density, normal, and shear components, Wn and Ws, are calculated with the use of a formula 1. Here the problem arises. What values of elastic models should we take for calculations? Glue or metal substrate? Therefore, the formulation of local failure criterion uses the assumption that the strength energy density in a selected microvolume, including the joint, is the driving force of a delamination of the adhesive joint under the force action. For this purpose, microvolume simulation belonging to the glue and the substrate is conventionally selected on the joint, which is inside and along which slipping and delamination are prohibited. Formulas 3 can be used to find the effective values of the normal elastic models, shear model, and Poisson ratio for selected microvolume and plane stress state, where H prime and H second are the glue substrate layer thicknesses in selected microvolume. Index 1 corresponded to the glue, and index 2 corresponded to the substrate respectively. Assume here that the ratio between the values of thickness H prime and H second in selected microvolume is equivalent to the inverse ratio of the values of the normal elastic moduli of the glue and the substrate. Substituting 4 into 3, after simple transformation, we arrive at the following formulas for calculation of the values elastic modulus and Poisson ratio for the selected microvolumes. In figure 3, we can see diagrams of the optimized strain energy density of the adhesive joint. The equation of the approximating straight lines in figure 3 can be written as equation 6, where this and this are values of limit strain energy density up to and clear components at failure, table 2. In figure 4, we can see a graphical representation of the adhesive failure criterion 6. Conclusion, experiment with a modified air count device have been made with the variation of the load application angle. The analysis of the result has enabled us to formulate a linear failure criterion which takes into account the balance between the characteristics of the elastic properties of the adhesive and the substrate, and to plot a diagram of ultimate adhesive rupture energy. The diagrams can be used for plotting diagram allowing on the determined a safe stress state, not leading to adhesive joint failure. Thank you.
Thank you, Sergey. Thank you for the presentation. Is there any question? If not, I can just ask you just a curiosity. Yeah, it's a nice presentation, and structural adhesive are a very attractive joining technology. And my question is, I see that you did experiments under different loading conditions. And my question is, what kind of failure did you observe? I mean, adhesive or cohesive? Is there any difference between the different loading conditions you have analyzed? And in addition, with your method, are you able to simulate both type of failure or not?
Yes, we tested our samples in other temperatures is a room temperature minus 50 and plus 50 degrees Celsius. But this results of this experiment we will send to the Journal of Fracture and Integrity.
Okay.
What is your question, Other?
The question is that the failure mode is adhesive failure or cohesive failure among the different loading conditions you have tested.
Okay. In testing we have we used electronic microscope, and we see a shear profile and fracture profile with sliding at shear test and rupture on the when we have a test in tensile test.
Okay, thank you, Sergey. We will have a look to the paper you have submitted in Frattura Integrità Strutturale. Thank you again for the presentation. And we can, is there any other question from the audience? If not, we can move to the next one that should be 18, enlightening critical details of a standardized procedure used to determine a fracture. Sorry, I don't see the whole title. Is there any author for this paper? Or maybe I'm wrong. Sorry. So maybe I'm wrong. Yeah. The title of the next paper should be Influence of Electrode Wear on Fracture of Spot Welds During Shear Tension Test. Is there any author?
Yes, I'm here.
Yeah.
Can you watch me?
Yeah, not yet. Sergey, can you stop the share screen, the screen sharing, please? Do you hear us, Sergey?
Excuse me, Professor Maleta.
Yeah.
Did you just mention our presentation?
Yeah, that is, which one?
The Enlightening Critical Details. I have another program.
Yeah, maybe there is a problem. Yeah, it is. I did wrong. So the
so it is in the next session, right?
Yeah. So now according to the schedule, the presentation should be this one: influence of electrode wear.
Okay.
Yeah.
Okay, sorry.
If I'm not
just to be sure.
Yeah. Should be this one.
Okay.
Please help me if there is any. I'm not sure, but let me check again. So should be okay. Influence. Yeah, this one. Yeah, this one. Thanks.
Okay. Good afternoon to everybody. My presentation is entitled "The Influence of Electrode Wear on Strength and Fracture Spot Welds During Shear Tension Test." And particularly, this is a part of a wider work that is ongoing relative to the possibility to analyze the welding signal in order to find a possible relationship between such signals and spot weld quality. Particularly, the control of the weld quality in resistant spot welding process requires the knowledge of the weld nugget size and or the weld strength. However, a direct measure of the weld nugget size is not possible because it remains between the two sheets, and therefore the joint quality is normally being assessed through destructive tests. This has fostered the research activity toward the implementation of many indirect measurements methods for the evaluation of the joint quality. Many of them exploiting process signal curves and the non-destructive test analysis. And particularly, as you can see from this picture, electron wear generally is the most important reason in causing some defective joints, and particularly by inducing some voids inside the weld nugget, or in some cases is responsible of incomplete welds. That's why predicting electron wear through a multi-sensor monitor of resist spot welding operation can be quite important aim for evaluating properly the quality of spot welds during the process itself. And so the aim of this study was to correlate the welding signals with electron wear, and in turn to evaluate how the electron wear can influence the strength of the spot welds and their fracture mode. And to perform this analysis, we have performed several electrode spots on overlapped sheet for the automotive industry, and after a certain number of spots we have defined which was the electrode wear and extent, and which was the corresponding quality of the spot weld by measuring the weld strength through traditionally shear tension test. And so overall, what we did is, after making all this spot welds, we obtained also some shear tension test samples, and from that we can evaluate which was the strength of the spot welds, and at the same time which is the entity of the electron wear. Particularly the electron wear was defined through a carbon imprinting test that, as you can see in the following, allow to approximately identify which is the extent of the electron wear. So at the beginning, we performed some spot welds with new electrodes. We performed initial shear tension test. After that, we performed a series of weld spots, and after a certain time, we defined the corresponding mechanical properties. And we repeat this operation over the time, and we defined which was the effect of the electrode wear on the mechanical property of the spot welds and the fracture mode. Particularly here, you can see a graph that summarizes which is the effect of the electrode wear on the shear strength of the weld spots. In particular, you can see that at the beginning we have used the new electrodes. You can see that after realizing the joints, we obtained quite high value of strength of the order of 10 to 11 kilonewton. Over the time, we have realized about 150 spot welds. We identified with the carbon imprinting test the extent of electron wear, and so the corresponding wear that occurred on it. And in correspondence of such situation, we defined also some spot welds. And these are the results obtained after this number of welding procedures. You can see that over the time, by increasing the number of the welds, the electrode worn particularly showing an enlargement of the cross-section diameter, and moreover a damage along the border of the electrode wear. You can see that after a certain time, the electrode was so worn that instead of having the traditional value obtained in the previous experimental test, we obtained a large scattering of the mechanical strength of spot wear. In some cases, we can find the highest strength value, but in other cases, you can see that the strength was very low. Particularly here, you can see which was the fracture mode obtained after sound joints. Particularly here, you can see the classical fracture of spot welds through a polar fracture that is characterized basically on the fracture of the heat affected zone around the weld nugget with a traditional ductile fracture. Instead, here you can see which was the problem related to the electrode wear, and particularly related to the fact that electrode with this level of wear was responsible of incomplete welded joints with a cross section that was represented by an unwelded area and welded area with some defects. For instance, you can see even if the fracture was ductile in this region of the spots, in other region there were many voids characterized by this typical surface appearance due to the final solidification in this voids. The aim particularly was to correlate some welding signals to these features, in particular to the mechanical strength and the fracture mode. At the moment, we have only examined the signal coming from the electrode indentation. You can see how the electrode wear and so the corresponding strength of the welds and the type of fracture can be related directly with electrode displacement, showing that for some joints we have a large electrode displacement in respect to a worn electrode. So this is due to the fact that worn electrodes can promote higher interface electrical resistance with different electrode displacement. In particular, the aim was also to examine the other signals in order to correlate during the welding process the manufacturing process and the type of joints obtained. I have concluded here. Thank you.
Thank you for the presentation. It is a very nice topic. Is there any question? If not, I have just curiosity. Did you try to analyze the results, to better analyze the results of mechanical strength of the welds by numerical simulation? For example, by using, I don't know, for example, cohesive zone and so on?
We have examined the weld strength by using SORPAS software. SORPAS software is a software devoted to spot welding. And at the moment, I cannot show you the results, but basically the software is able to demonstrate the fact that there is a certain coherency with electrode wear that we simulated by building up the electrode inside the software simulator, because it can only consider wear only by changing manually in the software the shape of the electrodes. And at the moment, we have some promising results, but we need to match better the welding signal with the numerical simulation, because at the moment there are some not proper matching between them.
Good. Thank you.
It's not easy to simulate the electrical resistance through the material at an interface and so forth. So there is a time to set up properly the numerical simulation.
Yeah, I see. Okay. Thanks again. Thanks again for your presentation. And now, if I'm not wrong, we can move to is there any other question? We can do.
I'm here.
We can move to the last one.
Yes. Can you hear me? Can you hear me? Mi sento? No?
Yes.
Yes, I can hear you.
We can hear you, Francesco.
Hello?
Hello.
Okay. So, hello everybody, and I'm Francesco Leoni, and in this presentation, I will show you the results of this preliminary finite element assessment of residual stresses in the similar aluminum steel butt weld joint produced with the novel welding technique I-bond. So the motivation was to see how the parameters, the different parameters used in the welding process affect the residual stresses, since experiments will be run using different welding speeds. And in this figure, you can see a schematic plot, a schematic drawing of the tool. What? I can't hear anything. Well, I hope you can hear me. Can you? Okay. I don't hear anything, but okay. So here is an example of an aluminum steel joint that was produced with this novel solid state welding technique. And in this table, you can see the different welding speeds that were chosen for this investigation, and that will be used for experimental tests in the close future. So as you can see, the model was done by employing two different materials, as well as a steel backing plate to account for the heat conduction with it. The main challenge in simulating this novel welding technique is that this is a friction-driven welding technique, and thus the heat that is generated during welding is caused by friction between the tool and the material that is joined, which is similar to what happens in friction stir welding. But in this case, you have to take into account also for the material which is added to the joint. Indeed, as I show you in this figure, there is an open groove between the materials that are joined, and this groove is filled with a material that is extruded inside the gap. So to analyze the heat generation, which is generated by the friction and the hot material that is introduced in the system, we used a semi-analytical model first in MATLAB that took into account of the welding condition, and basically consider the material properties at the tool matrix interface, and considering the sticking conditions, it calculates the torque and thus the power that is generated at the interface, and as well as the hot material contribution. And once the convergence is achieved, it gives as output the power in watt, which is then sent to the finite element code, which was Weldsim, which calculates the thermal field during the process, and finally the thermal stresses and the residual stresses in the joint. So this is an example of how the temperature field changing the welding speed. As you can see, in the lower velocity, the temperature field is wider, and this is observed also in these graphs, which are graphs of the temperature in the two materials, steel to the left and aluminum to the right, for the three conditions. And as you can see, the temperature drops as the welding speed increases, but this effect is lower than that of that will be observed for fusion welding, where you can keep constant the power by adjusting the power of the electrode, and thus the residual stresses are here finally plotted. And as you can see, there is a small area in the steel that is plasticized, and this is due to the high temperature that that the material undergoes at the vicinity of the interface. And instead, in the aluminum side, the plasticized zone is a bit wider, I would say, and this phenomenon is to be expected for the three welding speeds, since a wider zone for lower speed comes from the fact that the temperature field is wider for lower welding speed. So to conclude, those preliminary finite element results will be used for future investigations, where experiments will be run. So this is basically what we studied, and thank you for your attention.
Thank you, Francesco. I'm sorry, but I experienced a network connection before. Okay. Is there any question from? So, as far as I understand from your presentation, you are able to overcome most of the technical difficulties that are usually experienced during dissimilar welding. And this is a very interesting result. Just a quick question. Did you consider in your model the effects of diffusion of spaces within the junction unit, within the welds?
Of the diffusion that causes intermetallic formation?
Yeah.
No. In this model, it was not taken into account, but we are going to consider it since there is we developed also a model to consider that, to consider the thickness of the intermetallic that will be formed due to the welding process.
Thanks. It's a very nice. Welcome. I will try to read something about it.
Okay.
Thanks again.
You're welcome.
So maybe we are, if I'm not wrong, we are at the end of this session, and we are almost at the end of the conference. Thank you, everyone, for attending this virtual session, and please do not miss the last one that is at the 4:30, maybe in less than 30 minutes. Thank you again, and I hope to have the possibility to meet you in person in one of the next IGF events in the near future. Okay? Thanks again.
Thank you.
Bye.
Thank you.
Thank you.
Estate preparado para ayudarme.
Hello, everyone.
Hello.
Hello. I think that
yes, hello.
I think that we can start these last sections of this wonderful Congress. And okay, my name is Paolo. I work at the University of Padua, and I'm very proud to manage this last session. I remind the authors that they have 3 or 4 minutes to summarize their work, and then 5 and 6 minutes for questions. So if you're ready, we can start with the first presentation. And the first presentation is titled Broadening the Amplitude of the Definition of Structural Integrity, a tribute to Galileo Galilei. This work is by Jesus Toribio. Please.
Okay, thank you very much, Paulo. I will try to share the screen. Let's go. I will try and share, compartir en Spanish. I hope you can see my screen. Can you?
Yes, of course.
Then let's start. Just a summary. I am Jesus Toribio from the University of Salamanca in Spain, but I wonder now I cannot go to the next slide. That's the problem. Vista previa. I don't. Okay. The title of the presentation is Broadening the Amplitude of the Definition of Structural Integrity. I wonder if I can, Juan, can you, because in my screen I can see your pictures. Juan. Let's try to hide them. ¿Cómo puedo hacer aquí? Okay. Broadening the amplitude of the definition of structural integrity with a final tribute to Galileo Galilei. You can see the old-fashioned logo of my university, but as this is a summary, let's go. Then next slide. I am going to divide the presentation into 6 very short parts. Introduction, from fracture to structural integrity. Our reflection number 3, material versus structure. 4, multi-scale approach, and a short conclusion. And finally, a tribute to the physicist, the Italian, the Tuscany physicist, Galileo Galilei. The aim of the paper is to broaden the amplitude of the definition of structural integrity towards a new concept of structural integrity. From fracture to structural integrity and historical perspective, in this history, the Italian group on fracture has a prominent role. Here I am showing a picture of the meeting in Anaheim, May 2011. The Executive Committee of ICF, International Congress on Fracture. In this meeting, a new global blunt description of the ICF Society was launched. The International Congress of Fracture, the World Academy of Structural Integrity, ICF-WASI. I try to emphasize that the concept of structural integrity was discussed in this meeting. Finally, this concept of ICF-WASI was not accepted in Beijing 2 years later. Then a reflection between the concepts of material and structures, material versus structure. Because we discuss about the role of material, many people prefer materials in the names of the society, as the American Society of Testing and Material. I do prefer structure, following the history of European Structural Integrity Society. Material versus structure, any material is a structure. Structure is a quite more general concept with a broader meaning and comprises also, for example, the structure of a Johann Sebastian Bach's fugue of a Beethoven symphony. And thus, not any structure is a material, but there are immaterial structures. For instance, in perlitic steel, ferrite cementite are microstructures, are really a structure inside the material. Then any material is a structure itself. But also we have immaterial structures. For instance, we have an approach to Johann Sebastian Bach. This is the book 1 of the well-tempered clavier. The macro structure is the fugue, and the microstructure is the subject, counter-subject, episodes, or divertimenti, beautiful Italian word. Let's go to a multi-scale approach to our concept of structural integrity in engineering. I propose the following concept from mega structural integrity applicable to bridges. This is the Puente del Pedrido Bridge in La Coruña, pre-stressed concrete. The engineering was Eduardo Torroja, or the Ponte de Infante Bridge in Porto. The engineering was one of the cleverest students I've ever had, Luis Matute. This is mega structural integrity. Also mega structural integrity, Akashi Kaikyo Bridge in Kobe, world record in the time of construction in Japan. Beautiful sunset in the Kobe Bay here with this bridge. Regarding macrostructural integrity, I am showing a picture of a fracture profile, a kind of Monument Valley profile, remember Ion 4, in a notched specimen of cold round perlitic steel. Going to the smaller scales, the microstructural integrity, we could examine also in perlitic steel, the so-called perlitic pseudo-colony. You have the border here in a heavily cold round perlitic steel with the scales of micrometers. But even at a final scale, we could propose nanostructural integrity. This is an enlarged view with 8,000 times magnification of a perlitic pseudo-colony. And here we observe the interlamellar spacing of the size of nanometers. This is really a nanocomposite. And even at a finer scale and in the especially aggressive environment we have to suffer in the last 2 years, nanostructural integrity, the objective could be breaking the structural integrity. This is a kind of treatment of SARS-CoV-2 coronavirus, a kind of therapy. And just to finish, a short conclusion, I propose this new innovative concept of structural integrity applicable to all length scales with different names. And finally, attribute to Galileo Galilei in the Dimostrazioni Matematiche, this beautiful picture of the cantilever with the load. With this picture, we can consider Galileo Galilei as the founding father or the founding grandfather of fracture mechanics and modern structural integrity. That's all. Thank you very much for your kind attention.
Thank you. So we have time. Sorry, we have time for a question from the audience, please. If there are no questions, I have a curiosity. First of all, let me say that Galileo Galilei was professor of mathematics at my university for 3 years. So I'm very proud to say that. Second, my curiosity is this idea to compare the music structure with material structure is a very intriguing idea. So my curiosity, how did you have such kind of idea?
Thank you for the question. I have such kind of idea because I play piano. I studied music up to the level of composition with Anton Garcia Brin. Recently, he died because of coronavirus, as so many deaths. And this connection I particularly enjoyed because it's the same kind of, this is the kind of immaterial structure. Even I have compared the structure of perlitic steel, ferrite cementite, with Don Quixote and Sancho Panza in the Quixote, or with Fray Luis de León, a Spanish poet and major professor at the University of Salamanca. Entrambas a porfía mezclan una dulcísima armonía in Spanish, and both voices fighting against each other, they fix and they mix the sweetest harmony. The mix between voices creates the counterpoint and the structure. Then the mix between different components of the microstructure of perlitic steel creates a very noble material, a very highly resistant material because of the contribution of a softer but tougher part, ferrite, and the less tougher but more resistant, harder part, the cementite. And this is the connection. I think we can broaden the concept.
Thank you very much. It's a good idea, a good intuition. The second curiosity is this. Your concept is on the hierarchy structure of the material from the macro scale to the nano scale. So I think that is very important, in my opinion, also to investigate the correlation between macro, micro, and nano scale. So did you consider the correlation between the different scale?
That's a very, very clever question. Thank you very much. You touched the key point. Of course, we investigated the correlation between different scales, but only for the topic of our main research line, cold drawn perlitic steels. And of course, the failure of a tiny component of maybe a lamella of cementite, especially in these weak areas, perlitic, the so-called perlitic pseudo colonies, those colonies in which the lamella are not properly oriented, and it produces during cold drawing especially high, tremendous, especially high local interlamellar spacing, anomalous. This makes the perlitic pseudo colonies weakest point from the fracture mechanics point of view, and the initiation of fracture, they initiate macro fracture in these micro units or nano units. Then the connection is very, very nice. Of course, we had the typical accidents during the 70s and 80s of the DC-10 planes, the McDonnell Douglas. A lot of airplane crashes were caused by the failure of a bolt connection, a fastener connection. The failure of a really, really small element causes the failure or the loss of the engine and the crash of the plane. This is a clear connection with the smallest scale and the macro, nano, even the giga scale.
Okay, thank you very much. Very interesting.
Thank you.
So thank you again. So if there are any question, if no question, I think that we can move to the next next work. The next work is called Specimen Size Effects on Brittle Fracture Properties of Steel for Buildings Subject to Huge Earthquake by Naoya Oye et al. So please, Jesus, I think that you have stopped sharing the screen.
Okay. Sorry. Other participants are sharing slides.
Yes. Okay.
Thank you.
Okay, you can start sharing your screen now.
Okay. Okay, thank you for your introduction. I'd like to start my presentation. Oh, sorry.
Okay.
Okay.
IT works.
Okay. My name is Naoya Oye, and I'm presenting from Japan. I'm a graduate student from the University of Tokyo. Skyscrapers have been built from the 19th century to the 21st century, and their heights have increased over time. As buildings have grown larger and the thickness of structural members has increased, the risk of brittle fracture has also increased. I conducted 3-point bending tests on 8 types of specimens with different notch depths and specimen dimensions, but only the notch chip shape was the same. Based on the experimental results and finite element analysis, I evaluated the effect of specimen geometry on brittle fracture initiation properties, assessed the validity of existing fracture criterions, and proposed a new fracture criterion strategy. First, it was found that the critical quasi-CTOD, which is a fracture toughness value directly obtained from experiments, decreases with increasing plate thickness or notch depth, probably due to the difference in plastic constraint. Next, when the critical Weibull stress was calculated from the finite element analysis based on the local approach, the Bellarmine model assumes an initial defect and considers only stress-induced crack propagation, while the Borden model considers the probability of small cracks in the brittle phase due to plastic deformation. In the Borden model, the cumulative probability of crack initiation is linearly related to the equivalent plastic strain, but this is modified in the Yossi's model by considering it as an exponent of beta. It was found that Borde and Yossi's models could evaluate the fracture toughness uniformly, modified from the original Bellarmine model. In order to evaluate the validity of these Weibull stress models, we defined the probability that a given volume element would be the fracture initiation point for the entire specimen by going back to the derivation of each local approach, assuming that the brittle fracture initiation point is limited to the longitudinal center of the specimen and the mid-thickness. The probability density function is treated as a function of the distance from the notch chip. By observing the actual failure location of each specimen using the SEM, the probability that the actual location is a failure location can be determined. This allows us to determine which Weibull stress model is the most likely in terms of failure fracture probability. As a result, the Borden model, which is a modification of the Bellarmine model, was found to be the most likely model. However, if the Borden model represented the actual phenomenon, it would admit the existence of numerous microcracks near the tip of the notch, and this assumption was considered highly questionable. Looking at the voids in ferritic perlite steel, we can see that they have a volume. From this fact, it was thought that the flow stress from various directions, that is stress triaxiality, might be involved in microcrack nucleation. Some previous studies have mentioned that an increase in triaxiality can promote brittle fracture and its elementary process, void growth. Therefore, we introduced the factor of triaxiality into the fracture probability and optimized gamma so that the fracture probability becomes maximum likelihood, and the increase in the fracture probability was confirmed. Although the introduction of the factor of triaxiality in this study was quite simple and the exponent was determined from the calculation results, at least the possibility that triaxiality is involved in microcrack generation was suggested. Thank you for listening.
Thank you very much for your presentation. We have some minutes for a question from the audience, please. If no question,
there is one.
Yeah, please.
Hello.
Hello,
Alexander Sedmak. What is the connection between your excellent introduction and excellent presentation of this micromechanical modeling? Because I don't see it at the moment. Can you explain? I mean, you presented these large structures and their potential failure of seismic, and then you talked about different sizes of the specimen, and of course you applied this micromodeling technique, but how do you apply this to large structures like Burj Khalifa?
So, okay. In fact, actually, we want to conduct a fracture test on actual size of test specimen, but it is, in fact, it is difficult to conduct fracture test on actual scale. So we need to draw accurate fracture initiation property from small specimens. And that is different scale from real construction.
Okay, so you will have to test real material to get some micromechanical properties and then to apply the techniques you presented. Okay, thank you.
Thank you.
Okay, I have a curiosity. I saw that you detected microcrack that was intergranular microcrack between perlite and ferrite. So I wonder if you have also detected transgranular microcracks in your microstructures.
Of course, fracture initiation point occurs also in grain, not only grain boundaries. But I think that fracture dislocation moves to the grain boundary. So in plastic deformation. So fracture initiation is occurs in grain boundary more frequently.
Okay, thank you very much.
Thank you.
Okay, we move to the next work. And the work number 3 is titled, An Overview of Laser Welding of Metal Forms, Techniques, Advantages, and Challenges. This work is by Girolamo Costanza et al. Please, the screen is yours. Is there some authors of this work? No, I didn't see any authors. So we move to the next works. The works number 4 is titled Fatigue Damage Assessment of Welded HDPE Details, Evaluating Their Energy Release by Dario Santonocito and others.
Thank you, Mr. Chairman.
Thank you.
I shared my screen. Okay, so thank you for the introduction. And the aim of this work was the assessment of the fatigue properties of high-density polyethylene welded specimens by means of energy approaches, such as the static thermographic method and the thermographic method. This was obtained by monitoring the specimen surface temperature with an infrared camera. As you are aware, the fatigue properties requires a large amount of time and material in order to be assessed, but by adopting the energy approaches, they can be retrieved in a very short amount of time. So the applied methodology is based on the static thermographic method proposed by Risitano and Risitano, and it consists in the assessment of the change of the linear slope between the phase 1 and phase 2 of the superficial temperature of a specimen monitored during a static tensile test. This change in the slope can be related to a macroscopic stress state, which introduces in the material the first microplasticization, hence leading to fatigue failure if we cyclically test the materials. We adopted, according to the ISO standard, welded high-density polyethylene specimens, and we performed 3 kinds of tests: static tensile test and stepwise fatigue test with an increasing stress level, applied stress level, and constant amplitude fatigue test, traditional fatigue test. And we monitored the specimen surface temperature by means of an infrared camera. As you can see, for the static tensile test, we can see a linear decrease in the temperature signal, and until a change in the slope, it is not easy. And we can make the intersection between the first phase and the second phase, assessing a stress level that can be related to the macroscopic applied stress level at which the first damage is introduced in the material. As you can see from the fracture point of view, the welded area is not affected by the failure. Secondly, we performed stepwise fatigue test with an increasing stress level, and we can see a negative temperature increase compared to the initial state for a stress level between 13.3 megapascal and 14 megapascal. So if we report the stabilization temperatures versus the applied stress level, and we make the linear regression of the 2 temperature trend, we can assess the fatigue limit by the thermographic method, the classical thermographic method. At the end, traditional fatigue tests were performed, and as you can see from the last slide, we have practically equal value of the fatigue limit, the same assessed by the static thermographic method and thermographic method are near 14 megapascal, while the classical fatigue test with a probability of survival of 50% is equal to 13.5 megapascal. So at the end, we can assess in a very rapid way the fatigue limit of such material in a very short amount of time. Thank you.
Thank you for this very clear presentation. We have time for questions from the audience first. The word rapid is a very beautiful word because time is money. So I was always fascinated by these methodologies to calculate fatigue strength by rapid method using variation of temperature. So I have a question, a curiosity first, if there are no questions from the audience. My question is this methodology, can this methodology be applied to also metallic material? Because I wonder, you apply this method to a polymeric materials, and we know the inner friction in polymeric material are very high. So it is very easy to find a variation of temperature because of this stress load or fatigue load applied to the specimen. But it is not the same thing for metallic material that are characterized by high conductivity and very low internal friction. So my question is, can this methodology be applied also to other material families?
Yes, of course, because we have to think that this methodology was applied at first on metallic materials, and but it mainly depends on the kind of steel that on which we are applying this methodology, and we applied it on medium carbon steels as well as very low carbon steel materials, and we obtain wonderful results because the signal temperature was a really clear signal, and in addition also to polymers and composite materials. And I think also that this methodology could be very useful on 3D printed materials such as polymers or metal, because as we are aware, by changing some of the printing parameters, we obtain a different kind of materials, totally different. So it is very important to assess in a short amount of time the fatigue properties of the materials.
Yes, I agree.
This methodology has a long way to the material characterization, especially for 3D printed materials.
Yes, I agree. Is there an influence of the frequency of the load?
Yes.
Because I suppose that the frequency, by varying the frequency, the variation of temperature also varies.
Yes, because as you can see from the graphics, for this kind of materials, we adopted a frequency of 1 Hertz in order to not increase too much the temperature, because maybe we can reach the glass transition temperature of the material.
Yes, polymers, yes.
Yes, as well as on composite. But on the other hand, with steel, we can work with higher frequency, I think 10 or 20 Hertz. And so we can reduce the testing time.
Okay, there are any issue in preparing the setup of the test? I wonder if there are any issue in the calibrating the thermal camera.
No, because we adopt the relative temperature increment relative to the first thermogram of our investigation, It is important to have a specimen with an high emissivity surface. And as you can see, this kind of specimens is black, but in general, we have to paint the surface with a black paint in order to increase the emissivity of the material. But in general, is really easy to perform this kind of test.
Very interesting. Thank you very much again for your work.
Thank you.
I think that we have time for a question again. If there are any questions from the audience. If there are no questions, I think that we can move to the next presentation. I ask you to stop sharing the screen. Thank you very much.
Thank you.
Okay, the next works is called Preliminary in situ study of FIB assisted method for aluminum solid state welding at the micro scale. This work is by Ambra Celotto and others. Please,
hello,
Ambra.
Everyone. Thank
Hello,
you. I'm sharing. Can you see my presentation? Here we are. Okay, good afternoon, everyone. I'm Ambra Celotto. I'm a PhD student at NTNU, and my main supervisor is Prof. Filippo Berto. And the work I presented was about a method for cold welding of aluminum inside a FIB microscope. A FIB microscope is nothing more than a scanning electron microscope equipped with other tools that allows different procedures. First of all, we have a focused ion beam, which allows a different perspective by imaging on the sample. It is able also to mill out material particle on the sample. Then we also have a gas injection system that allows chemical vapor deposition onto the sample. And above all, that is the most important for my work here, the OmniProbe needle, which is nothing more than a tungsten needle that allows us to manipulate small material pieces inside the chamber. So with these tools, what we did is to try to develop a method for welding two different aluminum alloys together at the solid state. So here you can see the experimental setup that turns out to be useful for our purpose. It's not actually the designed one, the initially designed one, but it's the preliminary step of this work. So here you can see the micromanipulator, the OmniProbe needle, that is pushing towards this aluminum wedge onto another aluminum alloy base material plate in an oxide-free area, which was milled. The oxide was previously milled out from this area. So here you can see the real-time video, and what we can appreciate is the high plastic deformation that occurs both in the filler metal and in the base metal. So by this, we identified a possible bonded interface, which is here, and then we went to analyze this interface by cross-sectioning in a perpendicular plane. And what we have seen is this boundary between the expected two materials. And here we could see the difference in grain size that allows us to identify the two different materials. And with the magnified picture, we were able also to detect the bonded interface and also some dispersoids in the filler material side, which are quite typical for the filler metal considered. We also carried out some EDS analysis to be able to state that actually what we are imaging here, they are two different materials. And so, of course, this is not a complete research, because we need to, first of all, to develop a more systematical technique, which can be reproducible and can allow to extract some specimen from the joint interface, and then test these joints. So we are going to do tensile tests and eventually compression in tests, everything of course at the micro scale. And the plan is also to carry out some electrical conductivity measurements on the bonded interfaces. So this was the summary of our work, and if there are any questions,
Thank you very much, Ambra. This last picture didn't appear in your presentation.
Yes, you're right. I actually realized that maybe it was better to also for the discussion to present what we are going to do.
Okay. So we have time for a question from the audience. No questions? Okay. It's time for me. I have a curiosity or a question. The first is, did you think that it's possible to move to TEM investigation using the specimen you obtained?
Actually,
analyze the interface.
Yes, TM analysis are actually part of the main project. This is carried out by the physicists in our team, and so the ones more that has more expertise with the TM analysis. But yes, the main aim of the project is to. Here I showed just the method for welding two aluminum alloys, but the main objective of the project is to try to weld at the solid state, at the micro scale, aluminum and copper, which are expected to form intermetallic compounds. And thus, there, the TM analysis will be very useful to understand how this bonding mechanisms occurs and which are the intermetallic compounds that are formed. And so basically understanding the bonding mechanism, it's yeah, in overall.
Yes, understood. Thank you. Thank you very much. I have another question. I didn't understand how the hybrid needle failed. It failed by buckling, in a buckling effect or bending effect, because I saw that the failure occurs in the welding parts of the hybrid needle. So
you're right.
Yes, I wonder if you have some improvement in the project, in the design of the hybrid needle in order to avoid this kind of a failure.
Yes, thank you for the question. It was actually the thing that we are trying to improve. And as you can see, as you have seen from my presentation, yeah, the first experimental setup was to create this hybrid needle to be pushed against the base metal plate, and here we can see the failing. And I think in this particular case the failing occurred because of the scarce bonding between the tip, the aluminum tip, and the tungsten needle. But also I think the material that has built up in the base metal plate here act as a barrier to the to the tip to be pushed against the plate. And so I think it's a mixed reason between a mixed, how to say, yeah, the reason is both the buckling of the tip and also the poor welding between the two parts. And actually what we are trying to develop now is this new setup, which the hybrid needle will be pushed quite perpendicularly to a hole that is dig in the base metal plate here. And we are trying to mime this simulation here. And we expect that this setup will enhance the shear stresses on between the filler material tip sides and the hole sides in the base plate. So, and
yes.
also this setup can prevent the bending. So.
Yes, I think that this new configuration will works better. So good luck.
Yeah, thank you. We need them. We need that.
Okay, are there any question? Any other question, please? No other question. So I think that we can move to the next presentation. Thank you very much again, Ambra.
Thanks to you. Have a nice day.
Okay, the next work is called Applying the Dual Adhesive Technique for Strength Improvement of Bonded Joint. This work is by Ferreira et al. So please.
Yeah, hello, good afternoon. My name is
Good afternoon.
My name is Raul, and I will do the presentation, the resume presentation. Okay, are you seeing?
Yes.
Yeah.
We can.
Okay. I'm doing the presentation applying the dual adhesive technique for strength improvement of bonded joints. The main objective of this work is to determine experimental and numerical the step adhesive joints composed with two adhesives for various overlap lengths. We studied 4 different overlap lengths: 12.5, 25, 37.5, and 50 millimeters. The materials used for the adherence was the aluminum alloy, and the adhesives are the AV138 and 2015. The main advantage of the step latch joint are the decrease in peel load forces and also the decrease of the stress gradients. And the main disadvantages are the difficulty in machining, bigger manufacturing time, and more expensive manufacturing process. Okay. The dual adhesive technique, the main characteristics are the joints that can withstand high and low temperature applications. This kind of dual adhesive try to improve the stress distribution. Normally, a more stiff adhesive is used at the center, and more ductile are used at the edges. Here are presented the experimental Pmax curves, so the maximum strength, and also the failure energies that are presented here, the experimental determination of the failure energies. In the case of, these are all compared, the dual adhesive with the single adhesive, okay? And for the failure energies, for the case of 50 millimeters, there's a more bigger difference in the failure energy for the adhesive 2015 because there was some plasticization of the adherence. In terms of the numerical work, the numerical simulations were performed in the Dabox software, and here are some specifications of the elements and the mesh size. In terms of the comparison between the numerical and the experimental regarding the strength of the joints, an overall good agreement was observed, and also for the numerical failure energies, also a good agreement was verified. The main conclusions are that in this particular dual adhesive configuration, it is not possible to observe a significant improvement of the joints when compared to the single adhesive. And the use of mixed joints is only favorable in particular cases because the combination of two adhesives may increase or decrease the bond strength depending on the overlap length. So this is the resume presentation. Thank you very much for your attention.
Thank you very much. Thank you very much for this very interesting work.
Okay, thank you.
We have time for question.
Yes, of course.
Are there any questions from the audience? Please. I worked on adhesive in my thesis.
Okay.
With,
so you understand what we are talking about here.
Yes.
I'm also finishing my PhD in the adhesives now, also in the adhesive area.
Yes, I work above all with the stress singularities induced by the interface between the two materials.
The critical aspect of adhesive bonds.
Yes. Okay, if I have some curiosity, the first one is how did you model the fracture mechanism?
Sorry, can you repeat? I didn't understand quite well your question.
Yes, sorry.
Sometimes it fails.
How did you model? How did you model the fracture mechanism?
Oh, with the cohesive elements of Avox software. Okay, with the finite element software.
Okay. The second question. Yes. Where the fracture started? Where does the fracture started in the mixed joints? Because you use two different kind of adhesive, one brittle at the center part and two other plastic adhesive. So my question is, where does the fracture started?
In this case of joints, okay, the step-lapped joint, it started the fracture at the edges of the overlap length, okay, because it's the area where it's more stressed, okay? There's higher stresses here.
Yes, it's correct. Yes, it was only a curiosity. Thank you very much again for your presentation.
Okay, thank you very much for your time, for your attention. Stop sharing.
Okay, so we can move to the next one. The next one work is called Structural Assessment of Monocoque Frame Construction using finite element analysis, a study case on a designed vehicle chassis referring to Ford GT40. This work is by Iliam Widianto et al.
Yes, thank you. I will share my screen.
Yes, please. The screen is yours.
Can you see my screen?
Yes. Yes, you can start.
Okay. My name is Ilham Widianto from 11 Maret University, Indonesia, and I will explain about structural assessment of monocoque frame construction using finite element analysis, a study case on a design vehicle chassis referring to GT40. The introduction, the advantage of using space frame chassis is construction are the mass of the structure is lesser and cost effective than other the types of chassis, but due to the complicated manufacturing process. The space frame chassis, the platform is only used for high performance and niche market cars. Due to the chassis frame's unique design, the engine is wound as low as possible to achieve a low center of gravity for improved handling and cornering. And next, it's about methodology. The simulation use finite element methods. We have 2 points important. There are chassis criteria and chassis specification. The chassis specification can be seen in the table on the right side. And the chassis criteria, we have two simple objectives. There are less weight and more power. Each of these has the simple effect of improving the power to weight ratio and accelerating performance, and then improving the power to weight ratio and accelerating performance. And next, the analysis result can be seen in the following slide. We focus on 5 analysis results. There are found stress, component strength, displacement, reaction force, and safety factor. The result of the G240 chassis has a minimum found stress of 9.082 multiplied by 10 to the power of negative 8 megapascal and a maximum of 181.7 megapascal. And the result of the minimum value is located at the y-axis of negative 6.649 multiplied by 10 to the power of negative 4, and the maximum is located at the y-axis of 3.179 multiplied by 10 to the power of negative 4. And the maximum magnitude displacement of the G240 chassis is 0.441 millimeters. The maximum magnitude reaction force is 548.9 Newton, and the maximum safety factor is at the 15 and the minimum at the 1.14. Thank you for the attention.
Thank you. Thank you for your presentation. I ask the audience if there are any questions.
Yes, I have curiosity.
Yeah?
Yes,
Please.
I have curiosity. Okay. Hello, everyone. As most of us already know that Ford GT40 is a legendary car, and it's also filmed on Ford versus Ferrari, and it also won Le Mans race around 60s. So my question is, why did you take Ford GT40 as your research object while this car is already very famous? Okay, thank you.
Okay, thank you for your question from Faiz Zulfikar. In 1966, Ford joined the 24 Hours of Le Mans, and they focused on engines, transmission, and chassis. It all added up to a properly concentrated operation focused on one thing. At the end, they winning on the competition. That's what make us interested in examining why this happened, especially in terms of chassis. The chassis use monocoque models, but they adopt with space frame models. The space frame models have advantages, as I said earlier on the second slide. Thank you.
Okay.
Okay, thank you.
I have a curiosity or a question. Did you think this work can be applied also to advanced high-strength steel? Because I suppose that using advanced high-strength steel, we can reduce further the weight of the chassis. Did you
Sorry,
understand?
can you repeat that?
Yes, I can. I repeat my question. Do you think that this work can be also applied to other kind of steel? For example, I mentioned the advanced high-strength steel in order to have a further reduction of the weight of the chassis.
Okay. Why use the steel materials when the 1966 the material steels can use the regular chassis on that car, but the important the steel can be reduced the weight and the ratio of the ratio of the machine, so they can be stable on the circuit.
Okay, thank you very much. And another curiosity, which code did you use for your numerical analysis? Which numerical code did you use?
Okay, the numerical to use I use finite element method and from the geometrical meshing, I use parabolic element order.
Okay.
And the average element size, I use 15 millimeters.
Okay, thank you very much.
Thank you.
Are there any questions? Any other questions? No? So we can move to the next presentation. Ilham, please stop sharing your screen. Thank you very much.
Thank you.
Okay, the next presentation is the next word. Sorry, is called enlightening critical details of a standardized procedure used to determine the fracture toughness of brittle structural materials. This work is by Ermioni et al. Please.
Thank you, Mr. Chairman.
Thank you to you.
Okay.
Okay.
Do you see the full screen?
No, we see your screen, but not in the presentation mode. But it is
now.
Okay. Now you can see in the presentation mode.
Okay. Good afternoon, ladies and gentlemen. The present study describes a purely experimental protocol aiming to enlighten some critical details of a standardized procedure usually used to determine the fracture toughness of brittle structural materials. Notched straight through Brazilian discs made of Dionysos marble with a central notch were studied. The front surface of the discs was monitored by the two cameras of the 3D DIC technique used during the whole loading procedure, and 4 acoustic sensors were attached at the rear face of some specimens. These are typical low displacement curves, one curve for each class of specimens. And it is seen that almost all of them have exhibit some low drops, one or more. Let's focus on a typical specimen of the second class. This photo was taken right after the fracture of the specimen. We can see at the upper part of the disc a unique crack along the loading axis, while on the contrary, at the lower part of the disc, there are 2 cracks. So we tried to find out from which crown of the notch cracking started. And we studied the distribution of the strains along the horizontal axis developed on the disc. And it can be said that the crack starts from the lower crown of the notch while a few seconds later, intense strain field also appears at the upper crown of the notch. Both fields become longer and longer until the fracture of the specimen, while right afterwards, secondary cracks were also appeared. But we always have in mind that the specific marble is extremely brittle, and we also have in mind that the cameras have a finite resolution. So, okay, we detected the point from which a crack started, but at which point, at which time instant? Two small areas on both sides of the lower crown were isolated, and their displacement along the horizontal axis were plotted versus the time of the experiment, and also their difference. And we obtained this graph, which can be clearly divided into 3 stages. The first slope change observed is about 1,000 seconds, and or in other words, about 70% of the maximum load for the specific specimen, and we assume it corresponds to the initial formation of the crack front, while the second slope change to its propagation. Indeed, this seems to be right based on the slope change observed on the cumulative energy recorded from the acoustic sensors at the lower part of the disc. We see that the rate of increase is detected at the same time instant, and it is about 200 seconds earlier than the respective slope change at the upper part of the disc. Coming to an end, it can be said that the curved jaws of the ISRM standard impose some restrictions on the specimen, and this make the detection of cracking rather difficult, not only by naked eye, but also using a high-speed camera. In this case, DIC was very helpful to understand the fracture process, and it's extremely useful the fact that the load at which the specimen fails seems to be much smaller than the maximum load attained, and this smaller load should be the one that should be used for the determination of the fracture toughness. And of course, when we can apply different experimental techniques, of course, we should do it because we gain more information. Thank you very much for your attention.
Thank you. Thank you for this very interesting work. I ask the audience if there are any questions. If no question, I have a curiosity. Did you assess the values of fracture toughness using this experimental technique?
It's the next step.
Okay.
And we try to apply also other experimental techniques to gain more information, and not only the acoustic emission one.
Okay, because in my opinion, it would be interesting to compare the result of fracture toughness coming from this kind of test with other results coming from other kind of tests. It would be very interesting. Another curiosity. Did you think to use failure criteria in order to model this experimental test? For example, criteria based on strain energy density, other criteria, factor criteria?
Yes, of course, the modified Griffith criterion as a first step. And we have a lot of work to do in the future.
Okay. Good luck.
Thank you very much.
Thank you again for this very.
I have a question.
Okay, there is a question from the audience, please.
Hello, Noni.
Hello, Professor Sedmak.
Do you plan to also to involve numerical analysis like finite element method, which could help, if not for the experiment itself, which is comprehensive and excellent, but maybe to finite element method itself to check their applicability for this complex problem, because to simulate concrete behavior or heterogeneous materials like you do experimental is not easy.
Yes, numerical analysis is already made and it was presented a few days ago, but it was mainly for, there is YouTube.
Okay, I'll check it.
But it was mainly focused on the parametric analysis and also to validate the model based on the experiments and also based on analytic solution, not only the finite elements.
Yeah, that would be very nice combination of analytics, numerics, and experiments. So I'm looking forward for the next Mediterranean Fracture Mechanics Conference in Athens and to see new results.
Thank you. We are looking forward to you.
Okay, thank you very much again for this very nice work.
Thank you, Mr. Chairman.
So we can move to the last presentation of this Congress. And the last presentation, the last work is called Assessment of Design Midship Section Structures Subject to Hydrostatic and Hydrodynamic Loads, a Convergent Study. His work is by Muhammad Akbar et al. Please, Akbar, thank you very much. We can hear you. We can't hear you. We can't hear you.
Hello. Hello.
Hello. Okay.
Hello, my name is Muhammad Sabiqullah Akbar from Department of Mechanical Engineering, 11 Maret University of Indonesia. Now I want to present my paper. The title is Assessment of Design Midship Section Structure Subjected to the Hydrostatic and Hydrodynamic Loads, a Convergent Study. As you know, around 71% of Earth's surface is covered by oceans. So the water transportation, such as a vessel, is the most important transportation. As the demand of the ship transportation increase, the loads on the whole structure increase as well. The structure design should be achieved two main objectives. The first one, the strength of the ship structure is very important to withstand the load of the ship. And the second one is the structure should be designed at a considerable cost. This paper discussed the numerical study using a finite element analysis of a midship structure with a different outcome for each ELT ratio, referring to benchmarking paper. The material that we use for the simulation is titanium alloy. This material is also used in benchmarking studies by Raja in 2018, so we can compare it. And for the material properties, as you can see over here in the table, for the geometry, the study tests the midship section of a 120 meters container ship with a given static load and dynamic load. As you can see the geometry over here. And the element length to thickness ratio value is obtained by the element size divided by the thickness of the geometry. The LT ratio of the simulation are starting from 5 to 11. The detail of the LT ratio you can see over here in the table. And for the boundary condition, it is important to equate the boundary condition and the loading in a massive structure to achieve outcomes that are comparable to benchmarking study, so we can get the right result. For the result, displacement ratio is the result of displacement analysis value divided by the displacement benchmark value. The closest result is when the LT ratio value is 10. The displacement is 26.94 millimeters, and the error is 3% compared to the displacement value of benchmarking study. The strain ratio is calculated by dividing the strain analysis value and the strain experiment value. The closest result when the LT ratio value is 7, with the error compared to benchmark study is 3.5%. And also the stress von Mises ratio is obtained from the stress analysis value divided by the stress benchmark value. The closest result when the ELT ratio is 7, with the error compared to the benchmarking study is 1.9%. Overall, the LT ratio value of 10 is the closest value to the benchmarking analysis, which has an average disparity of 11.16%. So for further research, it's recommended to use ELT ratio value of 10. Thank you for your attention. That's all.
Thank you very much. We have time for questions from the audience, please. If no question, I have curiosity. Did you perform an elastic analysis or an elastoplastic analysis?
Can you repeat it again?
Yes. Did you carry out an elastic analysis, numerical analysis, or an elastic plastic numerical analysis?
Okay.
Because I saw only elastic properties. Yes. No.
Oh, this one.
Previous one. Yes. The Young modulus and the yield stress is correct. So.
Okay. For this simulation, I use the elastic analysis.
Okay. And then elastoplastic analysis, I wonder if it is planned for the future, or you think that it is not necessary.
Can you repeat it again? I'm so sorry.
My question is, did you think that it's not necessary to perform an elastoplastic analysis according to your results?
I think it's not really important because it's not until the failure state, so it's only the elastic.
Okay.
Yeah.
My second question is this. I saw that the lower the number of elements, the higher the convergence. So it is very strange for me because in my experience, I found the opposite. So in general, we're using finite element models. The higher the number of elements, the higher the convergence.
Yeah. Okay. It's also because the geometry is really big, and that's why I also make the element it's quite big, and for to compare it to the LT ratio, compare it with the thickness of the geometry also.
Okay. Thank you very much again. Before ended this last section, I ask to the authors of the work number 3 if they are present. The work number 3 was an overview of laser welding of metal forms. Are there any authors? No, if no, I think that we can finish this last sessions. So I give the last words to the president, Francesco, and then to the new president, Professor Filippo Berto. Thank you very much to all the participants. Thank you very much to all the authors for these very interesting sessions. And I hope to see you face to face in the next meeting. Thank you very much again.
Thank you, Mr. Chairman.
Thank you.
Okay, Francesco, the screen is yours.
Can you hear me now?
Yes.
Yes.
Okay. Thank you so much, Paolo. And it is my pleasure to tell you that I am not the president now of IGF, and for your pleasure, the next president will be Filippo. So I'm not sure he is now here, but I hope so.
Yes, I'm here.
Ciao, Filippo.
Ciao.
Just a few words from me as old, or less not too old, but old president, and just some numbers about this nice conference, this great conference. We had more than 160 presentations. The 30% was from Italy, and the other 70% was from 25 different countries. We will publish a procedure issue, I hope, with all these presentations, and the deadline will be July 15, but I will send you many emails, don't worry. And we will publish 4 or 5 different special issues. More or less, all of you will be invited to send your contribution to these special issues. This is an evident success. So for this success, I wish to warmly thanks, first of all, the 3 invited speakers, Jose, Livio and Donato, for their really interesting presentations. I would like to obviously thanks all the chairmen. In this format, the chairmen play a key role because they have to watch all the presentation in order to obtain a exciting and interesting discussion. Obviously, I wish to thank our 2 sponsors, TechLab and MTS, for their support to this event. And obviously, I wish to thank all of you, the speakers, and all the people that wish to join us, both in the Zoom room and online in our streaming, because of you are also able to stream our presentations, our discussions, I must say, on YouTube and Facebook. Now I can see on my screen many different friends, Noni and Stavros, Alexander, and many other friends. It's always a great pleasure to meet, at least in remote, but I hope soon in presence, because I want to touch you. So frankly speaking, it is very hard to be so far all the time. So I want to eat with you the wonderful chocolate ball with Alexander, or the so fantastic. I want to watch Noni and Stavros dance in this wonderful way, because they are simply wonderful in dancing. Obviously, also as a researcher.
We also look forward to meet all of you again.
So thank you so much for being here. And so the last word to our new and wonderful, younger IGF president. And so Thank you all.
Congratulations.
Congratulations, Filippo.
So thank you so much. First of all, I want to thank you, as Francesco did, for participating to this IGF, and also I mean we will organize soon in presence event. I hope all together, and we have also this MedFract that was quite successful that we can probably remake soon if the COVID will disappear. But first of all, before to start to think to new events, I want only to thank a person that has dedicated 12 years to this society with huge efforts and with a lot of dedication. Of course, he's not died. He will. I
am leaving. I'm leaving.
Don't blush.
No, he will be still the engine of this society with me and others. But I want to thank Francesco for this huge contribution, not only to the IGF. I mean, the IGF has reached this level due to him, and I mean, I want to thank him a lot for this opportunity that I feel very heavy for me. So thank you so much to Francesco.
May I say something?
Yes.
Of course.
Congratulations to IGF. You are certainly the best in Europe. And I have also to emphasize Francesco's role. As far as I see, he set bar very high, but then again, I'm quite sure that Filippo will jump over it. So all the best for Italian friends.
Yeah, thank you so much. We will do our best like a team. So I think that is the key of success, as we did in the past in different roles, but working together. So I think that is the key for the future. So I'm very, very hopeful that we can maintain this standard and we can provide a good service to the society. So I want to thank you again, and I hope that we can meet soon and we can make a lot of things together as a group. I mean, as an extended IGF group, because IGF is not alive without the support of international friends like you that are always attending our conferences. So we are very proud to have important people like you and important friends like you that are always supporting our society. And I want to go ahead on this track with the help of Francesco and all the other members of the ESCO of IGF. Thank you so much.
Thank you.
Thank you. Ciao, see you soon.
Yes. So Francesco, you can officially close.
No, it's up to you. It's up to you.
I mean, we can, if any other want to say something, we are open to listen and to say hello to a friend that want to say something to us. If not, I think we can simply close the event.
I just want to give you my greeting for next year's events. Next year it will be 40 years that we created this group, and that's all. That has been almost all my life. Thank you.
Thank you, Donato.
Thank you, Donato. Thanks.
See you soon. Ciao.
We can close.
Ciao. Ciao.
We will meet soon in presence. Thank you. Thank you so much.
Bye-bye.
Bye. Bye. Bye.
Thank you. Bye.
Bye. Bye. Thank you.